Dear students, grade 12. This is the fourth part of equilibrium. Let's take a look at the learning outcomes in this video. So first we have to work out what is the value of pKa and the relationship between Ka and pKa. Explain and describe the titration curves. There are 4 types. Discuss which indicators is or are used or suitable for an acid-base titration. Define what is buffer solution. Explain how buffer solution can control the change of pH. Calculate the pH buffer solution from given appropriate data, acidic, buffer, and basic. And you can use also the Henderson-Hazel-Lage equation. First, let's remember some things about the previous lessons that you have studied. We previously studied about the water ionization equation, right? And we learned how to calculate the concentration of hydrogen and the concentration of hydroxide for both weak and strong acids or bases. Remember, you had the methods. Okay. Also remember, and before I forget, from learning the concentration of both hydrogen or hydroxide, we can learn or we can deduce the value of pH. So also remember that pH equals the minus logarithm of the concentration of hydrogen. And Kw, which is the constant dissociation of water, equals the concentration of hydrogen times the concentration of hydroxide, and it's a constant that equals 10 to the power of minus 14. So the concentration of hydrogen equals the concentration of hydroxide equals 1, and this is when it's neutral. Okay, like water, for example. Okay, now we're going to learn what is the term pKa. And first, let's answer this question. What is the relation between the pH and the concentration of hydrogen? This is an important question because later you will know why. So the relation between the pH and the concentration of hydrogen, as the pH gets lower, this means that the concentration of hydrogen is up. So let's put it this way. If the pH decrease, means the concentration of hydrogen increase. Just as simple. But what is pKa? pKa is used to make the value of Ka, which is the dissociation constant, more manageable, means more realistic. So pKa equal the minus log of Ka. Okay? So to calculate the pKa, you need to calculate first the Ka, as we learned in the previous videos. This is used for weak bases and acids. The pKa bears exactly the same relationship Ka as pH, right? So the pH is the minus log of concentration of hydrogen. The pKa is the minus log of Ka. So this is an example of some acids, their Ka and their pKa. For example, hydrofluoric acid. Hydrofluoric acid have a constant dissociation equals 5.6 times 10 power of minus 4 mole per diameter cube. The pKa, which is the minus log of Ka, gives that value. Okay, now look at that value and you can tell me what you notice. Okay, notice that as the acid gets weaker, actually the value of pKa also increase. So actually this is the opposite directly. So The weaker the weaker the acid, the larger the pKa. So this is the acid strength, or in another way we can say it's the concentration of hydrogen. So when the concentration of hydrogen decrease, the pKa increase. Okay, how can you tell that? Okay, hydrofluoric acid, methanoic acid, ethanoic acid, and hydrogen sulfide. Hydrogen sulfide is H2SO3. Okay, and hydrofluoric acid here, the Ka is 5.6 and the pKa is 3.3. So look at this pattern and tell me which one is the weakest acid. This is the weakest acid. Okay, because it has the larger pKa value. Now it's easy to see the trend. Okay, weaker acids, as you go down the table, and try to remember that now, the lower the value of pKa, the stronger the acid. So if the pKa is small, this means that it's more acid. Okay, see the relationship? It's inverse. So when the concentration of hydrogen decrease, the pKa increase. When the concentration of hydrogen decrease, the pKa actually drops. There. The lower the value of pKa, stronger acid. So less Ka, here, less Ka, more acidic. High Ka, less acidic. Okay, notice that also the Ka has a unit, which is mole per diameter cube, but pKa actually doesn't have a unit. Okay, let's try this example. Two different acids have the following pKa. So you have 3.24 and acid D 5.66. Which one is the strongest acid? Remember, concentration of hydrogen increase, so the pKa decrease. And the concentration of hydrogen decrease, the pKa increase. Simple as that. So if we need to know the strongest acid, we need the one with the lowest pKa. Strong acid means more concentration of hydrogen. So if you have more concentration of hydrogen, this means that you're looking for less pKa. Okay, guys, is it clear? So from this case, you have the winner, which is C. So acid C is stronger acid because it has less pKa. I think that's simple, right? Now let's move to another new completely objective away from the calculations. You have that. A titration. Remember, you have heard that word many and many times ago when you studied science in your early grades. So a titration actually is a chemical reaction in which you add acid and base. It's also known as the acid-base reaction. But in this case, we're talking about the titration. Let's make it more defined. The addition of an acid base of no titration to an acid and base which is of unknown titration to determine the concentration. So this is adding an acid or base which is known as the concentration is known to another acid or base which has unknown concentration to determine the concentration of which. is unknown, whether it's acid or base. To use that, we need an indicator. Okay, do you remember an indicator? An indicator is a chemical substance that is actually change its color when it's reacting with acid or base. An indicator is used to show the neutralization has occurred because actually it changes the color in acidic medium, basic medium, and even in neutral medium. You can use, there are many different types of indicators. There is the litmus paper as an example, but this is limited because it only can define if it's acid or base. But you have different or variety of indicators like methyl orange, phenolphthalein. You have the pH or the universal indicator, and you can use actually the pH meter, which give you the result actually from 1 to 14, and it's more specific because it's digital. It doesn't depend on the colors. So a titration result can be represented by curves. So you can use that data from the titration, the results that you have. In analytic chemistry, actually you make the experiment more than once and you take the average reading for each attempt you make. Okay, this makes it more accurate result. So in titration results can be represented by 4 different curves. The titration curves. In the titration curves, it shows the pH. The titration curve shows the pH titration curve shows the pH of solution changing during the acid-base reaction. How does the pH change along the reaction? And you have 4 types of titration curves. This is the first titration curve, and this is when between strong acid and strong base. Kids, you just have to learn the shape of the titration curve and just accompanied it with the type of reaction. So that shape of curve is the titration curve that represent the strong acid and a strong base. The neutralization point in that curve is actually close to 7. Okay? So here is also an important note. You have to keep these in mind. These are very important. When you have a strong acid reacting with a strong base, the neutralization point at 7. Okay, because it's strong and strong, so they neutralize when the pH reaches 7. If you have strong acid with a weak base, so the acid is strong, you have to guess the acid is stronger, so the neutralization actually happens, but less than 7 because it's more acidic. If you have a weak acid and a strong base, the neutralization point, now you have to think, just connect strong base, so the neutralization point will happen and it's more than 7 because it's more basic. But what if you have weak acid and a weak base? Actually, the pH, normally it should be 7, but it's very hard to determine. So this is the shape of the first titration curve. That shape is for strong acid and strong base, and the neutralization point is 7. And this shape represents the strong acid and strong base. This is the same one. Also, the neutralization point here is at 7. This is the titration of strong acid and weak base, and we said it will be less than 7. See, this is less than 7. See, guys? So it's more acidic. This is for weak acid and weak base, so it's here. It's difficult to determine. Weak acid and strong base, see? It's more than 7. Okay, this was our video for today, and hope to see you soon.